This conference will now be recorded.
Hello students, today we will be concluding wave optics. So as you can see in the title, today we will be discussing the rest of the portions of the polarization. As we have started polarization yesterday, we had discussed in the yesterday's class what is called polarization, what is polarized light, what is unpolarized light, how do we pictorially represent them, and what is polarizer, and how to polarize the light with polarizer, etc. we have discussed. And we have discussed that after, say, if you have an unpolarized light, after polarization the intensity of the light decreases. Okay, so those things we have discussed. Today what we are going to do, we are just going to learn a few things more in this polarization part. One is details of Malus law. This gives the intensity of the light intensity of light. When you analyze it, light has to pass through the analyzer. Okay, so we have seen when we see through analyzer, there is a variation in the intensity of the light when the analyzer is rotated. So this will give you the variation of intensity at different angle between the pass axis of polarizer and analyzer. I'll discuss, when I discuss, you will understand better again. Okay, so this we'll discuss in detail how it happens. Then we'll learn how sunlight gets scattered, or sunlight gets polarized by scattering. Okay, by scattering happens where? In the atoms or molecules, or maybe tiny particles in the sky. Okay, so due to scattering, the sunlight gets polarized. We'll discuss that. So this I have given a title as polarization by scattering, and then we'll see polarization by refraction. Polarization by refraction. See, this spelling polarization, Z and S both are used, so don't worry about this spelling. If I write Z, you can write either Z or S as well. Okay, so polarization by scattering, polarization by refraction, and Malus law, these three things I'll discuss in detail today, and then we'll discuss few numerical problems in this discussions. Okay, all right. So in this figure, I just want to recap a little bit. See, in this figure, this is unpolarized light. Can you tell me what these double arrow lines are representing? These are representing the electric field vector, or I can say component of electric field vector, component of electric field vector oscillating in plane vectors oscillating in plane. Okay, oscillating in plane of the paper or plane of the screen itself. In plane, I'm writing in plane. Okay, and these dots are representing the electric field vectors oscillating, sorry, vectors oscillating in a plane perpendicular to perpendicular to the plane of the paper. Okay, so these are two light vectors, and in a completely polarized light, either these electric field vectors which are oscillating in plane, or the electric field vectors which are oscillating out of plane or perpendicular to the plane will be present. Okay, only one type of electric vector will be present in the polarized light. Okay, and in case of unpolarized light, both the electric vectors will be oscillating, like vectors will be there. If I just draw maybe a two-dimensional, okay, so if I have, see, electric field vectors which are oscillating in the, suppose this is y, this is x, this is z. So the electric field vectors which are oscillating in the xy plane, okay, and some will oscillate in the, see, y direction. That means these are actually, so these are oscillating out of plane. So upon polarization, both of them will be actually separated from each other. Okay, in a combination, in unpolarized light, they go or they travel in combination, but when we polarize them, for a completely polarized light, we'll see one type of electric field vectors. Okay, only either electric field vectors which are oscillating in plane, or maybe this. Okay, so that we had seen already yesterday. See, this is a polarizer here, P. See, the path axis of this P is actually this one. You can see that this is the optic axis or path axis. This is called optic axis of the polarizer, optic axis or path axis, because it allows to pass the light rays which are having, or electric field vectors which are having their oscillations in plane. Okay, which are oscillating in plane or oscillating in a plane parallel to this optic axis. So that's why this axis is called path axis or optic axis. And see, this is the analyzer we had seen yesterday. See, this unpolarized light. So unpolarized light has, suppose, intensity I. So polarized light will have little bit lesser intensity. See, if it is completely polarized, then you would get I by 2, because half of them will be oscillating in the perpendicular direction, which will be absorbed or will not be allowed to pass through this polarizer, since its optic axis is not allowing the other vibrations to pass through. Now this intensity I0, see, I by 2, let me take this as I0. After polarization, the intensity of the light is I0. Okay, then when we have analyzer and polarizer having their path axis parallel to each other, see, this one and this one, they are parallel to each other, then intensity will not vary. Intensity will not vary. It will be same I0 which is seen through the analyzer. Now if the analyzer or optic axis of the analyzer is rotated about the direction of incident ray, this is the direction of incident ray, then we see intensity variations. Okay, intensity variations, intensity will be sometime, see this I0 will be completely zero sometime, and it will be sometime this intensity will be non-zero, sometime it will be zero, etc. We'll see. Okay, all right, so what I'm trying to say is that intensity varies. So this is what we are going to discuss today, how intensity vary when this the angle of the polarization, see angle of the axis, optic axis of polarizer and analyzer. Suppose this is analyzer, this is polarizer, optic axis. If they make an angle theta, okay, if this make an angle theta, this path axis, then intensity will be something like I0 cos square theta. So this is what we are going to discuss. This is given by an Malus or Malus, whatever you spell, okay, by an Malus, and it was actually given 1809. Okay, 1809. All right, let us go with our today's session. So that is, see, Malus law says, Malus law or Malus law, okay, whatever. If a completely plane polarized light is passed through an analyzer, the intensity I of the transmitted light varies directly as the square of cosine of the angle between optic axis of polarizer and analyzer. As I said, see, this is stated in terms of statement. See, if a completely plane polarized light pass through an analyzer, the intensity, the new intensity I will be directly proportional to, see, it will be varying directly proportional to the square of the cosine of the angle between the optic axis of the polarizer and the analyzer. Okay, this is statement. So this is okay. So the proportionality constant is to be I0, which is the highest intensity just to get after polarization. Okay, before entering to, see, I have polarizer, I have unpolarized light. Okay, unpolarized light, I have polarizer here. So suppose here intensity is I, here I'll get intensity I0 by 2. Okay, let us say I0, which is I by 2. Okay, okay, so I0 is I by 2. Yes, so this will be I0 by 2. This is the first polarized light. Now if you have analyzer, which you have path axis along this direction itself, then your light will have intensity same as I0. But if you rotate it, if you rotate the optic axis, then intensity varies significantly. Okay, that is what we have seen. And the intensity of the light which we get after the analyzer will be obtained from this Malus law, and mathematically this law is actually written as I is equal to I0, sorry, cosine square That means cos square theta. Okay, so this is what is the statement of Malus law. Now we have to prove this. See, we will just see from here. See, suppose this is the unpolarized light, as you can see, unpolarized light. So unpolarized light has intensity I, suppose, and suppose it has, so all right, so you can understand that intensity will be less than this unpolarized light. Anyway, let me tell you one thing. Let us take let us take that the amplitude of the polarized light, let the amplitude be E0. So this is the amplitude of the polarized light, amplitude of the polarized light. So this is amplitude of the polarized light. Okay, so this is the see, this is the polarized light. Okay, this is the polarized light. It is passing through the polarizer, so it is polarized light. And see, this is the analyzer. Let us say the analyzer has its path axis which makes an angle theta with the path axis of the polarizer. Path axis means optic axis. Okay, so if suppose the analyzer, see in this case the red line is the direction of the path axis of the analyzer, which is making an angle theta with the path axis of the polarizer. Now look, I can have this light, I can have two components of this light. Okay, this has amplitude, suppose I E0 after reflection, sorry, after passing through the polarizer. Now I can have two components of this light. See, this is the E0. I can have a component along this path axis of this. See, this is the optic axis of the analyzer, this blue one. So I can have two components of this light itself. So since this is E0 intensity, sorry, amplitude of the light, see, I can divide, or I can take component of that is E0 cos of theta here along this optic axis of this analyzer, and the another component E0 sin theta, which is perpendicular to the optic axis of the analyzer. So this light will be absorbed, or this will not be passing. Only the light which is parallel to the, like, electric field vectors which are parallel to the optic axis of the analyzer will pass. So E0 cos theta. So this is the amplitude of the light. See, we have, see, intensity and amplitude ratio as this, isn't it? So if I0 is the intensity of this light, then see, this intensity and amplitude has this relation. Intensity is equal to, or intensity is directly proportional to the square of the amplitude. Okay, so now here, see, what will the intensity then? Intensity at this position. Okay, what will be the intensity? I have to find out that. So that is, suppose I. Okay, so I will be directly proportional to E0 cos of theta whole square. That means what? If I just bring a proportionality constant, k is 0 square cos square theta. Okay, and what was the intensity of this light? Polarized light intensity was k is 0 square itself. Okay, this is suppose I0. Okay, intensity of the polarized light. Okay, now this I can write as I0 then. I0, and this is cos square theta. This is I. So this is what is actually called Malus law. This is the mathematical form of Malus law. Okay, so I is equal to I0 sine square theta. So this theta is the angle between the polarizer, optic axis of the polarizer, and the optic axis of the analyzer. Okay, so this is Malus law. Now see, if I want to see the intensity variation according to Malus law, see, intensity is actually directly proportional to cos square theta, that we have seen, right? Now if we plot with respect to angle, see the polarizer, so this is the polarizer optic axis, this is the analyzer optic axis, and suppose this optic axis is rotated. Okay, if this optic axis of the analyzer is rotated, then theta varies, right? Theta varies from all that from 0 to 90 degree to 180 degree, then 270 degree, and 360 degree, etc. So look here, if I draw this intensity just by see, this can be a very nice laboratory work if you just have an analyzer and polarizer, a set of analyzer and polarizer, then you can do this experiment very well, and you can see there will be intensity variation. So we know now by mathematics, okay, or solving things, that intensity varies, and how intensity varies, that can be given by the Malus law. Okay, so this Malus law here, okay, so this is the Malus law. Now look this graph, see at theta is equal to 90 degree, at theta is equal to 90 degree, that means this one, if the analyzer becomes like this, then he cannot, okay, so then the intensity will be 0, because you know polarizer has path axis like this, so light will be like this, and there will be no light which will be oscillating in a direction perpendicular to this. Okay, so that's why we will see at 90 degree we will see 0. At 180 degree, see cos square, cos of theta means what? Cos of theta is -1. Okay, so cos square of theta, which is here, see at 90 degree angle it is becoming minimum, at 180 it will be maximum, or at 360 it will be maximum intensity. Okay, 270 it will have minimum intensity, and 90 and 0. Okay, so this is how, see, there will be a question actually in NEET paper. I have seen this graph will be directly given. You have to choose along with other 3 graphs, you have to choose the correct answer. So you can remember this formula. In fact, it is coming from this mathematical formula, so you can just all right. So we have understood this will be the intensity variation of polarized light when it is seen through an analyzer. Okay, all right. Now we'll learn polarization by scattering. First of all, let me tell you what is this scattering. Anyway, you know, if we look a clear sky through a Polaroid one kind of polarizer, market, see, commercially available polarizer, these are actually Polaroids. They have a chain of molecules which will be in a particular direction, they will be arranged, and that will act as path axis, and other direction will be so, which is okay. So if clear blue sky is viewed through a Polaroid which is rotated, the rise and fall of intensity of light will be observed. Why, you know, why is it that? This is because of this polarization of the sunlight. Okay, in general, sunlight will be unpolarized light, because it has electric field vectors oscillating in all possible directions. But you know, when it incident on the molecules or atoms in the environment, then what happens? See, in the atomic model, we'll be learning. See okay, so atoms will have electrons, okay, in the cells. So when sunlight falls on this, sunlight has it is actually electromagnetic wave, so it has electric field. So light is electromagnetic wave, so it has electric field. Now here there are electrons also in the cells, outer cells. There will be electrons, and those electrons will be influenced by this electric field of the sunlight. How will that be influenced? Because see, electric field gives or exerts a force on the electric charges, okay, and because of this force, since electric field is oscillating, so the electrons also will be oscillating here. Electrons also will be oscillating, okay, electrons also will be oscillating, and these oscillating electrons further they will be actually radiating light or electromagnetic wave or electric field, whatever you say. So this is actually the scattering, phenomena of scattering. But one thing you have to notice that since electric field in the sunlight has two kind of vibrations, one in the plane, another one is out of plane or perpendicular to the plane. So what happens, suppose this is an atom, okay, this is an atom. So if the sunlight gets scattered by this atom, and when we see or view this scattered light in a direction perpendicular to the incident direction of the sunlight, okay, so we have to view from the perpendicular direction, okay, we have to view from a direction which is perpendicular to the direction of incident light. Okay, so this is an atom which is scattering light. See, I'll tell you, just a minute, I'll just drink some water and come. Excuse me, I'm back. So we have discussed how how sunlight gets scattered by atoms in the atmosphere. So atoms have electrons and sunlight has electric field vector. So it will exert a force on the electrons, and those electrons will actually oscillate since the electric field also oscillating. Okay, so along with the electric field vectors or electric field, the electrons will be oscillating. But electric field has two different vibrations, one along this way and another along this way. Okay, so some electrons will be oscillating in this direction, and they will be, so this is actually, suppose this is perpendicular, okay, this is perpendicular and this is in plane, okay, in plane, electric field which is oscillating in plane, this one. So when we view from a direction, see this scattered ray, when we view from a direction which is perpendicular to the direction of incident ray, then we see a completely polarized light with electric field vector oscillating in a direction perpendicular to the plane of the paper. Okay, I'll repeat this sentence once again. When sunlight incident on an atom, so light will be scattered, that is for sure. But when we see that scattered light from a direction perpendicular to the direction of the sunlight, this is incident direction and this is the direction I am viewing from, so this angle is 90 degree, then we see this scattered light will be completely polarized. Let us try to understand why this is completely polarized. You know, I have two components of electric field vectors, like two types of electric vectors which are oscillating perpendicular to the plane, another one is oscillating in plane. So this is in plane and this is perpendicular to the plane. Okay, perpendicular to the plane. So you know, the light, see the electric field vector which are oscillating in plane, they can radiate light in plane only. Okay, they don't have since they are oscillating, see they are oscillating in that particular direction, so their radiation will not be coming this side. Okay, only the component of the electric field for which the atom will oscillate, electrons will be oscillating in a direction perpendicular to the plane, they will again radiate light in this particular direction, this perpendicular direction. That's why, see this component, this parallel component doesn't have, see electrons which are oscillating in a parallel direction or like in a direction parallel to the plane will not be able to radiate light in this direction which has electric field perpendicular to the plane. Okay, plane of the paper. So that's why we see completely polarized light in this direction. If we see some other direction, maybe we'll see some other things. Okay, maybe mixed polarization or partially polarized light, or maybe this also we can see. So this is scattering by polarization. All right, now we'll see scattering by, sorry, I'm sorry, this is actually polarization by refraction. So this figure corresponds to polarization of light by refraction. See, in this case, when a light ray incident at the interface of two medium, suppose this is denser medium having refractive index mu, this is AR, has refractive index 1. Okay, mu AR is 1, refractive index of AR. So light is actually incident at the interface of a solid or denser medium and air. Now, as you know, since this medium is transparent, light will be transmitted, as well as some part of the light will be reflected. Okay, so it is seen that at a particular angle which is called angle of polarization, if I say this is IP, or sometimes this is called Bucher's angle also, or IB, at a particular angle of polarization, say a particular angle of incidence, when the reflected ray will be totally or completely polarized. This is reflected ray, completely polarized, completely polarized, this reflected ray. But what about refracted ray? This will be partially polarized. I'll explain the theory behind this. Okay, so when the angle of incidence is at all angle of incidence, it doesn't happen. Okay, polarization happens at a particular angle of incidence, that is called angle of polarization, or Bucher's angle also we'll see. So that angle of polarization, particular angle of polarization, the light will be refracted to the other medium, and at the same time some part of the light will be reflected. The reflected light will be completely polarized, whereas refracted ray, this will be refracted ray, this is refracted ray, this is refracted ray, which will be partially polarized. Refracted ray will be partially polarized and reflected ray will be completely polarized. And one more thing here we have to understand, that at this particular angle of polarization itself, this reflected ray and refracted ray, they makes an angle 90 degree. Okay, this is another thing we see here. Okay, when light incident on an interface, and it gets refracted as well as gets reflected also, some part of the light, incident light. But you know, if the angle of incidence of this light is the angle of polarization, then the reflected ray and refracted ray, they makes an angle just like critical angle in case of total internal reflection. So at this case, okay, this is kind of critical angle of incidence. So this is actually all about polarization by refraction. See, at this case, you know, this I can write. See, I'll just clean things here. Let me write, this is IP, incident light, and it is incident light is making an angle IP, which is the angle of polarization. So I can write Snell's law here. Look, Snell's law. We know this N1 sine IP will be is equal to N2 sine this. Let us say this angle is R. Okay. Now see the relation between R and IP. Okay, since this angle is 90 degree, and this IP, this also will be IP because angle of reflections are same. So IP, this IP plus R, this is actually 90 degree. This is total 90 degree, right? Now if we put here, see N1 is 1 anyway, N1 is 1, N2 let us keep like that. So N1 sine IP, sorry, N1 is 1, not 0. And N2 sine R, I'll write 90 minus IP, angle of polarization. So this means, you know, this is cos of IP. Okay, cos of IP, and you know you have here N1 sine IP. Okay, so we have got this. So what we got? We got mu is equal to R, N is equal to N is equal to sine theta by sine, okay, sine IP by cos IP. Okay, that means this is 10 IP. Okay, so this is actually, this angle is called Booster's angle. The particular angle of polarization, that is called Booster's angle. And so this is actually called Booster's law. Booster's law. Booster's angle we can find out Booster's angle IP, sometime it will be written theta p, etc. That is actually, so this is 10 IP. So I'm sorry, this is okay. So Booster's angle we have to find out sometime. So IP we have to find out 10 inverse of tan inverse of tan inverse of n. Okay, so this is actually Booster's angle, or this law is also called Booster's law. Okay, now we'll try to discuss few numerical problems on this polarization part. Not only numerical, we'll take some time some analytical problem as well, analytical questions as well. Okay, let us first uh, okay, I'll just write few questions back to back. Suppose question number 1, this is some analytical question. A polarizer is used. A polarizer is used to, options are reduce intensity of light, intensity of light. Option B, produce polarized light. Option C, increase intensity of light. Intensity of light. And option 4 says a polarizer is used to produce unpolarized light. Okay, So question is, see, using a polarizer is not having, okay, so to produce unpolarized light, this is not true. Increase intensity, this is also not true. Produce polarized light, this is obviously true, and this is also sometimes true, I can say, because in case of sunglass, okay, it actually is intensity is reduced, okay, by polarized spectacles, okay, all right, or sunglasses. So the most appropriate answer will be to polarize, to produce polarized light. See, light can be only polarized audio. Yes, I'm sorry. There was some network issue, so that's why there was audio problem. Anyway, I have not spoken anything during that time. Let me just do this problem. So the angle of polarization for any medium is 60 degree. What will be critical angle for this? What will be the critical angle for this? Okay. Okay. So the options are sine inverse n, option B sine inverse 1 by n, 1 by n, option C is tan inverse 1 by n, and option D is tan inverse n. See here, this is the angle of polarization, right? Angle of polarization is theta IP. We have a relationship, right? Tan IP is equal to mu, right? This is what we know. Mu or n here, refractive index n. So this question is actually connected to total internal reflection, because see here n is not given, right? So you have to find out critical angle for this. So this is n, right? You have to find out critical angle for this. All right. So let me go here. So IP is actually given as 60°. So tan 60° is equal to n. Okay, tan 60° is equal to n. So what is what is n? N is tan 60°. That means 1 by root over 3. This is root over 3. Okay, tan 60° means. All right. Now I have this relationship, right? N is equal to 1 over sine theta c. This we know. Or we can write sine theta c is equal to, this is for total internal reflection, sine theta c is equal to 1 over n. Okay. Now we can write this 1 over n as 1 over root over 3. Okay. So this is sine theta is equal to, so theta c is equal to sine inverse 1 over root over 3. Okay. So here I think I have written down the options for some other question. Let me correct this options. So this is sine inverse root over 3. Sorry, I'm very sorry. Okay, the option was, this was root over 3. Then let me erase this. Okay, let me erase the options. Options are given as following. For this, options are given: A sine inverse root over 3, option B tan inverse root over 3, option C cos inverse root over 3, option D tan inverse, sine inverse 1 by root over 3. So we have answer here. We had to find out from this condition, given things, angular polarization is given, so we can find out the refractive index here. Okay, refractive index from this, and then we can write down the condition for critical condition for the total internal reflection, that is sine theta c is equal to 1 over n. So this is the condition, right? So that from there we can find out this. All right. Okay, now I have another question. Refractive index of a material is equal to the tangent of polarizing angle is called Burscher's law, Lambert's law, Malus law, Bragg's law. We know that is Burscher's law. Okay. So this kind of questions are only there. I think, yeah, these are all for today. Yeah, so these are kind of questions you'll encountered. See, here is a question just to make you fool. Which of the following light is which of the following cannot be polarized? Cannot be polarized. Okay, so the options are radio wave, then option B says ultraviolet, light, or ultraviolet rays. Option C, infrared rays. Option D, ultrasonic wave. Ultrasonic. This is U. Ultrasonic waves. So which one it is? See, radio wave is electromagnetic wave, so it is transverse in nature. This is also transverse. Infrared is also part of electromagnetic wave. So these are all part of electromagnetic wave. Okay, EM wave. Range of like different portion of the spectra. Okay. All right. And this is actually ultrasonic wave is actually a sound wave. Okay, this is sound wave. So this cannot be polarized because it is not transverse in nature. Only transverse waves can be polarized. Okay. So this is the one which cannot be polarized. Okay, we'll stop it here for today. Next day, we'll take up JEE papers, but we will not do chapter wise. We'll take the full paper itself. 2020, as I had said, JEE main 2020 I'll take first, then 22, like that will solve in the classes. Okay, so I'll tell you the tricks also while discussing the solutions, and I'll give you the necessary formulae also. So thank you for your patience. Bye for today.